Hello, YouTube. Today we're going to be talking about time delays in process control. Next slide, please. So if you're watching this, you're probably already familiar with the general aspects of process controls and transfer function. And because of that, I won't go over what a transfer function is or how to derive one from the differential equation governing a process. But I will go over their relation to time delay. So let's look at a first order transfer function, which has the form seen here, 1 over tau s plus 1, where tau is the time constant. If we were to apply this to a system, then the response will appear immediately as soon as a disturbance is applied. So what that means is that as soon as you have a disturbance come into the system, the transfer function is going to output some change, which will appear immediately. However, in certain processes, you'll get a delay between the application disturbance and an output response. Or perhaps you'll get a delay in measurement. So an example of that would be a long pipe after an initial measurement. Another example would be if you use a measurement device that requires a long time to arrive at final output. So with a long pipe after the initial measurement, or it could be a long pipe after the measurement of the output, what happens is if you've got a concentration change, then you measure concentration, but then the concentration, the difference in concentration has to travel down, say, 10 feet of pipe. So that's going to take some amount of time. And because of that, in reality, you're not going to have an instantaneous result propagate through your process. Similarly, with a measurement device that requires a long time to arrive at a final output, you would, for example, a carbon dioxide meter, you would have some change that happens, but it isn't fed to a system response, and it isn't fed to a process control loop until sometime later. And so that also causes a time delay. And of course, you could have a myriad other reasons for having a time delay. For example, you could have a process component that responds by design gradually. A good example is water hammer valves. If you have a valve shut off, you want that to shut off somewhat gradually, because if you shut it off immediately, then you'll get what's called water hammer, which can be damaging to the system. And so for these reasons, you may end up with a time delay. Now, do you absolutely have to have a time delay modeled into your function? Well, not necessarily. You could simply model all time delays as transfer functions. For example, if you have some pipe flowing into your system, you measure it way upstream, then you can simply model the time it takes for the concentration to change down our pipe with the transfer function. So if you've got some pipe of constant cross-sectional area and you have some incompressible fluid, then you would apply a transfer function to that, and you would simply multiply that as a series with the transfer function of the main process. Now, why don't we always do that? Well, that's not always practical. For example, that could result in a very large amount of transfer functions, which would have to be applied to the system. If you have 30 or 40 transfer functions being applied to a simple mixing tank system, you can see that that's not entirely practical. You'd have to not only have the computational power to deal with said transfer functions, you also have to train the operator to be able to understand these transfer functions. And of course, you'd have to pay an engineer extra to develop more transfer functions. Next slide, please. So we've got a few methods of approximating time delay simply. For a small time constant, that is to say a small tau value, you can use a Taylor approximation. This approximation is derived from a Taylor series expansion. So if you've got some function describing, say, your long pipe of 1 over 1 plus tau s, then we can call tau theta naught. And that's approximately equal to the exponent of negative theta naught x. And so this e to the negative theta naught s can simply be multiplied onto your existing transfer function of your process, and that can help to model the time delay of your process. Now, what happens if your time constant is large? Well, you can still apply the Taylor method, but it becomes less accurate, and so it becomes desirable to use a more effective approximation. So for a large time constant, you would use what's called the paid approximation. You can see that in the middle here. And this paid approximation is the 1 minus theta over 2s over 1 plus theta over 2s. And so you would take this theta, which is, of course, going to be inputted as your tau, and you're going to calculate that out such that we can apply our time delay in a similar manner to the Taylor method, which is to say we would apply this again as simply being a multiplied e to the negative theta over s. So that's a little confusing. However, with practice, I think you'll get the hang of it. In a more general sense, you could use the Skogstad half rule. Now, the Skogstad half rule isn't really any singular formula. What it is more of a method. And what this method is you can approach your transfer function as adding half of the largest theta being removed, which is to say half of the largest time constant being removed, to the Taylor time delay of the smaller component being removed, and add the other half to the smallest remaining time constant. So all that means is that you're going to take the largest time delay, which is to say the largest time-consuming component of your process, and you're going to take the time constant and take half of that and stick it onto the existing time delay that you would get from the Taylor approximation, and then the other half just goes on to the remaining time constant, the smallest remaining time constant. Next slide, please.
So now we're just going to run through some examples to visualize what these formulas actually mean a little bit better. So we can see we're starting with the transfer function at the top with time constants of -0.1 in the numerator and then 7.2 and 1 in the denominator, and a k value of 1. And that's a ugly transfer function that if you have access to Simulink or some other similar software, you can plug in and it'll plot it fine. But as soon as you start getting more transfer functions in your process, or if you don't have access to those softwares as easily, you need to simplify it down a little bit. And so the easiest approximation to make for this function is just using the Taylor method, where you take the smallest time constants and add them together. So in this case, the 0.1, 0.2, and 1 are all significantly smaller than 7. So you remove those terms and take those time constants, add them together, get a theta value of 1.3. And that simply just becomes your time delay in the new transfer function. You can see G is now equal to e to the negative 1.3s over 7s plus 1. To get a slightly more accurate and general approximation for this process, you can use the half rule, which has a very similar beginning to it as the Taylor method, except in this case, the 1 tau value is divided by 2 and added to both the theta and the remaining tau. And so now you can see that the theta is, instead of 0.1 plus 0.2 plus 1, it is now 0.1 plus 0.2 plus 0.5, giving you a slightly smaller time delay of only 0.8, but also changing the remaining time constant from 7 to 7.5 with the addition of half of that largest time constant being removed. And so you can see the transfer function is now e to the negative 0.8s over 7.5s plus 1. And the final approximation you can use is the paid approximation, which a little bit more complicated math, but you can see it gets you a theta value of only 0.83, which is much smaller than the other ones given by the other approximations here. But the transfer function still has the same form of e to the negative 0.83 over 7s plus 1. And when all of these are plotted in Simulink together, you can see that all approximations, including the base function, approach 1 as time goes to infinity. As you can see on the left-hand graph, as time is going to 50, they all converge onto one line because they all have the same k value. But if we zoom into the beginning to see the area with the largest error between these approximations, on the right-hand graph where time only goes up to 10, you can see that because these time constants are relatively small, the paid approximation actually has the least accurate result because it is significantly higher than the rest and does not approach the remaining 3 lines until further on down the process. But the half rule and Taylor series both quickly approach the original transfer function with only minor errors in the very beginning of the process due to having different points at which the function kicks into effect.
Unfortunately, some processes are too complicated to easily model using these time delay methods. Some examples of these processes include material balances, energy balances, flow dynamics, physical properties, or thermodynamics. Additionally, in all of these past examples, we have been assuming a constant time delay term, e to the negative theta s. In reality, this is not always the case, especially when considering variable flow rates or multiple disturbances. Theta may not really be constant, and that breaks down any of the past approximations we've been able to make. Furthermore, these simplified models may not be accurate for compressible fluids or gases. In some cases, they may be accurate for laminar flow or non-Newtonian fluids, but extra caution must be taken. And in these much more complicated cases, empirical models can be very useful for determining process behavior. And these empirical models typically utilize least squares regression and computer software, which allows the analysis of almost any system. However, these methods can be much more time-consuming, require robust computer software, and a large amount of accurate data. Next slide, please. So in conclusion, many real-world processes, time delays are a very important consideration. They occur almost wherever material or energy are being moved. It can have a significant impact on the process dynamics. Therefore, it is important to be able to predict and understand the process response to time delays. Several simplified first-order plus time delay methods were introduced, such as the Taylor series, paid approximation, and the half rule approximation. And as we saw in a little case study, their accuracy was compared, and most of them do a great job of approximating much more complicated functions. Finally, it is important to realize that not all processes can be simplified by these methods. For more complicated or non-ideal systems, time delays may not be assumed to be constant. And in these cases, empirical methods using computer software are the preferred method and are typically more accurate, but this requires a lot of significant data in order to be able to do properly. Thank you.